Dmitri Mendeleev was born in a remote Siberian town in 1834, the youngest of around 14 siblings. The exact number is disputed. His brother reported that there were 17, but only 14 survived to be baptized. Misfortune struck early. The same year Dmitri was born, his father Ivan lost his eyesight and his job as a teacher. His mother, Maria, became the family's backbone, reopening her family's old glass factory to make ends meet. Calamity then compounded. When Dmitri was a young teenager, his father died, and a fire ravaged the glass factory, leaving the family destitute. These early hardships forged in Mendeleev a resilience and a determination that would shape his character and his career. His mother, Maria Mendeleeva, was determined to secure a future for her brilliant youngest child. In 1849, she embarked on an arduous trek with him across the Russian Empire, taking teenage Dmitri and 2 siblings on a 2,000-kilometer journey to Moscow in search of educational opportunities. The voyage alone, by horse-drawn carriage and rail through forests and over mountains, was formidable, a testament to his mother's faith in Dmitri's potential. But Moscow's university turned Mendeleev away, reportedly due to his Siberian provincial origins. Undeterred, the family pressed on to St. Petersburg, the imperial capital. There, Dmitri gained admission to the main pedagogical institute, a teacher training college turned university. Tragedy, however, was never far behind. Soon after Dmitri began his studies, his devoted mother Maria, exhausted perhaps from the journey and years of sacrifice, succumbed to tuberculosis, as did his beloved sister. Dmitri himself fell ill with that disease, but later recovered. Later in life, he dedicated his doctoral thesis to his mother's memory, honoring her guidance and sacrifice. Quote, "Conducting a factory, she educated me by her own word. To give me the cause of science, she left Siberia with me, spending thus her last resources and strength. When dying, she said, 'Be careful of illusion. Work. Search for divine and scientific truth.'" This credo of hard work and truth-seeking, instilled by his mother, became the lodestar of his career. Mendeleev graduated in 1855 and at age 21 took a post as a science teacher in Simferopol on the Crimean Peninsula. The move south was meant to help with his frail health and tuberculosis in a warmer climate. Fate had other plans. Within a week of his arrival, the Crimean War erupted, and the school where he taught was shut down as battles loomed nearby. Mendeleev was hastily transferred to another school in Odessa, but by 1856 he decided to return to St. Petersburg to continue his education. There he earned his master's degree and conducted research in chemistry focusing on the interplay of alcohol and water, a project he would later complete as his doctoral dissertation. Ever the hungry scholar, Mendeleev sought knowledge beyond Russia's borders. In 1860, he traveled to Germany to attend the first ever International Chemistry Congress held in Karlsruhe. There he mingled with the era's luminaries, legends, including even Michael Faraday in attendance. A pressing issue for chemists was standardizing atomic weights and chemical formulas, and at Karlsruhe Mendeleev found intellectual inspiration. Notably, he encountered a paper by Italian chemist Stanislao Cannizzaro, whose classifications on atomic weights left a deep impression. This meeting of minds in Germany planted a seed. If one could reliably quantify atomic weights, perhaps the elements hid an underlying order waiting to be discovered. Mendeleev returned to Russia, fired up with new ideas and a sense of urgency. He worried that Russian science lagged behind. At just 27 years old, he poured his energy into writing a comprehensive textbook of organic chemistry, distilling the state of chemical knowledge for Russian students. This 500-page tome, published in 1861, was so well received that it won the prestigious Demidov Prize and established Mendeleev as a rising star in chemistry. By the mid-1860s, he became a professor at the University of St. Petersburg, known for his charisma as a lecturer and his ability to inspire students. Yet, even as he taught, Mendeleev's restless mind kept turning back to a fundamental puzzle: how to organize the chemical elements in a logical way. By the late 1860s, the chemical world knew of about 63 elements, from lightweight hydrogen to hefty metals like lead. Scientists had noticed patterns. Lithium, sodium, and potassium, for example, all behaved similarly, but a unifying system eluded discovery. Mendeleev became obsessed with cracking this problem. He wrote each element's properties on cards and endlessly shuffled them, searching for a pattern as if working on a jigsaw puzzle. On February 17, 1869, insight finally struck. As Mendeleev arranged the elements in order of increasing atomic weight, he suddenly perceived that certain types of elements recurred at regular intervals. In that eureka moment, the periodic law was born. Elements with similar properties appeared at predictable intervals when arranged by weight. Mendeleev later described how, quote, elements arranged according to the value of their atomic weights present a clear periodicity of properties, encapsulating this profound order in nature. Legend has it that Mendeleev had been working tirelessly on the problem without sleep for days until the solution came to him in a dream, an anecdote he himself recounted to a friend. Exhausted, he dozed off at his desk and envisioned the elements falling into place on the table. Upon waking, he jotted down what he saw. In truth, Mendeleev had been pondering the idea for years since Karlsruhe, and the dream story may have been embellished. Nevertheless, it highlights how dramatically he perceived the pattern all at once. According to one contemporary account, on the very day of his breakthrough, Mendeleev was due to visit a local cheese dairy. He instead flipped over the dairy's invitation letter and scribbled his nascent periodic table on the back. He cut up these notes into cards and played a form of chemical solitaire, aligning and realigning the pieces until the logical arrangement was irrefutable. The result was the first periodic table of the elements, a grand synthesis of the elements into rows and columns, organized by atomic weight and chemical affinity. Crucially, Mendeleev's table had gaps, blank spaces, where no known element fit the pattern. He boldly proclaimed that they represented elements yet to be discovered. He even predicted the properties of these missing elements, giving them provisional names like Eka aluminum and Eka silicon, Sanskrit Eka meaning one beyond. This predictive power set Mendeleev's periodic law apart from earlier incomplete attempts to classify elements, and he was soon proven correct. Within a few years, newly isolated elements filled in the blanks. Gallium was discovered in 1875, exactly where Mendeleev had said Eka aluminum would be, and it possessed the density and atomic weight he had foretold. Scandium, discovered in 1879, and germanium in 1886 further vindicated his predictions. What had initially been met with skepticism quickly turned to astonishment as the scientific community recognized that the periodic table was a powerful tool not just for organizing known chemistry, but for forecasting new chemistry. Mendeleev, the once obscure Siberian boy, had rewritten the paradigm of chemistry and earned worldwide fame in the process. The periodic table alone would have secured Mendeleev's legacy, but his curiosity ranged far and wide beyond elemental chemistry. He was a polymath with a practical streak, eager to apply science to industry, technology, and everyday life. In the 1870s and 1880s, Mendeleev turned his attention to improving Russian industry and agriculture. He was the first to propose using pipelines to transport oil, an idea ahead of its time, and he helped establish Russia's first oil refinery. Always hands-on, he experimented with chemical fertilizers on his own farm and became a vocal advocate for modernizing agriculture through science, urging farmers to enrich their soils with nutrients. Eager to spread scientific knowledge, Mendeleev would travel by train in third-class carriages, deliberately sitting with peasants so he could dispense practical advice on everything from crop rotation to manure usage. This approachable egalitarian side of Mendeleev made him something of a folk hero in Russia, a professor who could come down from the ivory tower and get his boots muddy in the service of the common man. Mendeleev lent his expertise to the design of the world's first Arctic icebreaker, the Yermak, launched by the Russian Navy in 1898. His fascination with ships and navigation led him to write over 40 papers on shipbuilding and Arctic exploration. He applied scientific principles to help Russia conquer the frozen seas. Around the same time, the Russian Navy sought his help in developing new munitions. Mendeleev responded by formulating a type of smokeless gunpowder that he called pyrocolodion, derived from nitrocellulose. Although bureaucratic hurdles prevented his invention from being mass-produced, it was free of the instability problems plaguing other powders of the day. His contributions to naval technology underscored how versatile his scientific talents were. Mendeleev's adventurous spirit wasn't confined to the laboratory or the library. In 1887, at the age of 53, he took to the skies, alone in a hot air balloon, to observe a solar eclipse above the cloud cover. Despite having no prior experience ballooning, and also no idea how to land the contraption, the intrepid chemist could not resist the chance to gather data. He emerged safely from the escapade, earning bragging rights and exemplifying the fearless curiosity that defined him. Mendeleev was also instrumental in advancing scientific metrology, the science of measurement in Russia. After 1890, he became the founding director of the Bureau of Weights and Measures in St. Petersburg, where he modernized the nation's system of units, introducing the metric system to the Russian Empire and standardizing measures for trade and science. You will sometimes hear that Mendeleev was the one who defined what vodka actually was, at 40% ethanol to 60% water, though in fact this had been previously established before his work with the Russian government began. In his research on gases, he discovered the concept of critical temperature, what he called the absolute boiling point, above which a gas cannot be liquefied. This insight was foundational to the liquefaction of gases and later cryogenics. He even played a role in formulating the ideal gas law in its modern form by incorporating Avogadro's hypothesis to relate gas volume, pressure, temperature, and molecular number. Truly, his scientific contributions were as diverse as they were deep. His inventiveness extended to the very tools of science and ordinary life. Mendeleev devised improved instruments, such as a new type of barometer, and a volumetric flask for precise density measurements. He was a lifelong tinkerer. Famously, he was so fond of making things that he became known for crafting exceptional suitcases. Drawing on his chemical knowledge of adhesives, he developed a special glue and personally manufactured luggage that was the envy of his friends. In short, there seemed to be no field of inquiry or craft beyond Mendeleev's interest. He moved fluidly from pure theory to practical innovation, guided by the belief that science could serve society. Mendeleev's contemporaries knew him as a man of strong principles and intense passions. He could be genial and inspiring, but also stubborn and unorthodox. In his professional life, he was never shy about challenging the status quo. In 1890, when student protests erupted at St. Petersburg University, the 56-year-old professor sided with the students in calling for reforms. This did not sit well with the imperial authorities. As a result, Mendeleev was forced to resign his university chair that year. Unbowed, he transitioned to lead the National Bureau of Weights and Measures, turning his focus to public service and the betterment of Russian science infrastructure. He had glimpsed the future of chemistry, yet he greeted some new discoveries with skepticism. He was notably unconvinced by the nascent theories of ions and electrons, doubting the validity of Arrhenius's electrolyte theory and J.J. Thomson's electron. In the 1890s, when the Curies revealed the phenomenon of radioactivity, Mendeleev stubbornly rejected the idea that atoms could disintegrate, seeing it as an attack on the very concept of elemental stability. Ironically, decades after his death, scientists synthesized the element mendelevium, and it turned out to be highly radioactive. The man who ordered the elements would forever have an element named in his honor, even if nature had the last laugh regarding atomic theory. Mendeleev died in 1907 at the age of 72, revered as a national hero and an international icon of science. He had lived long enough to see his periodic table universally recognized as one of the great achievements in science, and he received many accolades in his final years, including the Royal Society's prestigious Copley Medal in 1905. When he succumbed to influenza, St. Petersburg gave him a state funeral attended by throngs of students and citizens. In a poignant tribute, a group of students carried a gigantic periodic table aloft in the funeral procession, a symbol of the profound mark Mendeleev left on science and education. More than a century later, the tale of Dmitri Mendeleev continues to inspire. His life reads like an epic, a sickly boy from Siberia who, armed with genius and grit, deciphered the hidden order of nature. He was a dreamer and a doer, an academic who could be a craftsman, a theorist who could be an engineer. Whether advising farmers in the field or debating scientific theory, Mendeleev brought a passionate intensity to everything he did. His periodic table remains a linchpin of modern chemistry, a testament to his insight, but equally important is the example he set as a scientist engaged with the world. And we'll finish with an addendum on the periodic table itself. The periodic table arranges over 100 chemical elements today. The periodic table's impact also goes well beyond chemistry. It has reshaped fundamental science. The success of Mendeleev's scheme bolstered the idea that atoms truly exist as real, distinct entities. In the 1860s, the concept of atoms was still somewhat controversial in science. Mendeleev's orderly table, with its precise predictions, provided strong evidence that elements behave as if they are made of uniform atomic particles with definite weights. In fact, when those missing elements, like gallium, turned up as predicted, it validated the then controversial belief in the reality of atoms. It showed that if an atom was merely a convenient fiction, it was an uncannily accurate one, enough to predict real substances. This helped convert remaining skeptics to atomic theory, firmly establishing atoms as the foundation of chemistry. Perhaps even more significantly, the periodic table hinted at deeper structures within the atom, foreshadowing the development of modern physics. Chemists noticed that the repeating patterns of element properties might be caused by something inside the atom that repeats periodically. This mystery drove scientists to search for an explanation, which eventually led to the discovery of the atom's internal architecture. In the early 20th century, the physicist Henry Moseley used X-ray experiment to show that an element's atomic number, the number of protons in its nucleus, is what defines its position in the periodic table, a discovery that resolved lingering anomalies and put the table on a firm theoretical foundation. Not long after, Niels Bohr and others explained that the periodic recurrence of properties arises from the way electrons fill different energy shells in atoms, an insight rooted in the new quantum theory. In short, the periodic table pointed toward quantum physics even before that field existed. It anticipated the mathematical rules governing matter that would later be revealed through quantum mechanics. This was a profound development. A chemical classification led to the discovery of entirely new laws of nature. By ushering in the age of atomic and quantum theory, the periodic table transformed chemistry from alchemy into modern science. Mendeleev's work came at the end of an era when some still searched for magic combinations of elements, like alchemists seeking to turn lead into gold. The periodic law helped banish that mysticism by showing that elements follow logical, quantifiable rules. And thus the table became a symbol of science's power to find hidden order in nature. It represents not merely the elements themselves, but the logical cogency and principled rationality of science, a reminder that even the great complexity of the material world can be organized and understood through human insight. More than 150 years after its inception, the periodic table remains one of the most important tools in science. Its value persists because it contains fundamental truths about matter in an elegant visual form. Chemists, physicists, and materials scientists all rely on the periodic table to understand and predict how elements will behave. By knowing that elements in the same column share certain characteristics, researchers can intelligently choose materials for new technologies. The periodic table stands as a shining example of human intellect, an idea people were initially very skeptical of that became an enduring foundation of modern science. It has even come to symbolize not only the building blocks of matter, but the rational spirit of science itself. From its humble origins as a handmade chart to its central role in cutting-edge research, the periodic table continues to enlighten and inspire, a testament to our ability to find order in the universe and use that knowledge to drive future progress.